these properties that are important for cavity applications. So first off, in terms of growing large area films, here it shows the original setup at Penn State that we used to make MgB2 film. All those very nice properties are made in this reactor that is heated by inductive heating, which limit the sample size to about 5 by 5 millimeters. So that's too small for many applications, for many measurements. So one goal is to scale it up. There has been an effort at Peking University in China that I collaborated with. They have used the resistive heater. And when you do resistive heater, you are not limited by the inductive heating. You can grow larger size. And they have demonstrated very high quality films and like a 15 by 15 millimeter area samples. And so the students who built this setup actually worked in my group before he did this work. And then he is in my group now. He was a postdoc and recently promoted to a assistant research assistant professor. So he will be with us working on this project. And so this is for 1.5 centimeter size. And our goal is to do the 2-inch diameter. So this is one of the approach that we will be just trying to scale it up and see whether the whole flow and everything still works. And the system has been set up at Temple. And this shows the cabinet for the reactors. When you open this door up, you can see that there are 2 reactors sitting next to each other that use the same gas handling systems. And the smaller ones is just same as that at Peking University. That will be good for 1.5 centimeter square films. And the bigger one will be used for, is designed for 2-inch diameter films. So we have already started producing films using the smaller reactor. So this is one of the first films on silicon carbide that shows the residual resistivity of about 1 micron centimeter and with a TC over 40 Kelvin. But of course, every system is different, so we have to fine-tune it to make the system more stable. And I mentioned one technique, just scale that system up for 2-inch films. And we're building also a new pocket heater for 2-inch films. And this is the schematics of this setup. And this idea is really inspired by Michio Naito in Japan. And so he came up with this very, very smart idea that that takes it's similar to what STI heater is, but it does not have all these openings, and it's much more compact. So for a 2-inch films, in the STI setup, you will need at least for a 5-inch large heater. But this, we can just have a 3-inch heater for this 2-inch films. And so we already designed this, and the machine shop is right now making it. So we'll be trying this very, very soon. So you might want to ask why we don't continue to use STI heater. There are some issues there that we're trying to avoid using exactly the same heater. And also the thermal mass of this heater is much, much smaller than the STI heater. So for people who do depositions, you would appreciate that the smaller the thermal mass, the better off your life will be. And so in terms of coating of cavities, as I mentioned, we will first trying to coat the 6 gigahertz niobium cavity. And the ideas we have is to do the in situ coating and introduce the magnesium vapor and diboride gas from two sides of the cavity, and they will see each other in this space, and then coat it on the cavity wall. To ensure the uniformity, we will rotate the cavity, and we will also move the cavity up and down to coat the whole coat the whole cavity. And this picture shows that we have this cavity. You see these fixtures. We decided that we need to cut the cavity up so that we know what we are depositing. If we deposit on the cavity, we don't really know what's inside, or we need to look at it. So we want to cut it in half and this hold it together. And this area is the heating tube furnace, and that will keep the whole area to the deposition temperature that we want. And we will have a magnesium furnace here that feeds the magnesium vapor, and we'll have this delivery of diboride from the top. And so they will meet somewhere inside of the cavity. And this is the picture of the so-called integrated HPCVD system that has two HPCVD chambers and a spotter system that's all connected with a transfer distribution chamber. And that system will be used for this purpose. And so that contains the vacuum chamber like this. It's like a square when you open the door, and actually it's a D-shaped chamber. And this shows the heater inside here, and this position corresponds to the position when you pull the cavity to the top of the heating the furnace, and here is when the cavity is at the bottom of that furnace. And we are still in the final stage of the design, and it's near finish. And once we finish the design, we will start making it. The other possibility of coating the cavity, in particular if we are coating larger cavities, we might try this two-step process. First, deposit the boron films, and then anneal this boron film inside of magnesium vapor. And so this is at least another approach that we can try in case the in situ process encounters some difficulties. The other thing is to establish some capabilities to measure the properties of these films. And we have established some collaboration with some Tayagi in Drexel University. He has this so-called low-field microwave magneto-absorption measurement, which has a microwave cavity, and inside a Helmholtz magnet. So what you can do is to measure the absorption of the sample while applying a magnetic field along the surface of the films. And so what he wants to see is when you increase the field, once the vortex enters the film, then the microwave absorption would increase. And from there, hopefully we can measure the HC1 of the films. And so he's kind of an old timer, and there's no electronic kind of things except for a chart recorder. So these are some of the data that's recorded for the first measurement. And so here I just traced it and flipped it. So you can see this is absorption of the micro-absorption as a function of temperature for 3 cases when there is no applied field, 1,000 Gauss, 1,500 Gauss of applied field. And so you can see that it starts to go up at different temperatures. And for 30, if there's no field, absorption starts to go up at 32 Kelvin, 1,000 Gauss, we have 30 Kelvin, and 1,500 Gauss correspond to 28 Kelvin. So if these are HC1, it's really, really very high values. So we were puzzled by that, and trying to figure out whether this is really true or this is something we're not understanding correctly or wrong. Because this would give you a slope of HC1 of 25 millitesla per Kelvin. And so, multiply by 30 Kelvin. This would give you something like, this will give you like a 700 or something, which we thought is too large. In particular, these films are 100 nanometer thick, and we know that our films normally have a thickness of 40 nanometers of penetration depth. So we are not completely understanding what this result means. So that's one thing that we've been working on. The other thing that we've done is to borrow a dielectric puck resonator from Steve Anlager at University of Maryland. And so we can use this to measure potentially measure the surface resistance at about 25 gigahertz. And we just want to have a way that we can screen our samples before we send it to the collaborators for characterization. And of course, once we have our large area film, we will be more than happy to send the samples to people who are interested in measuring these samples. So to summarize, I first talked about why we are interested in this magnesium diboride, the low resistivity and high TC, promised low BCS surface resistance, which could be lower than niobium. And we have the short penetration depths that promise a higher thermodynamic critical field. And the optimistic estimates will be something like 800 millitesla compared to 200 for niobium, although there are many issues that need to be studied to see realistically what will be the thermodynamic critical field. And so the current status of our research, in July of last year, I moved from Penn State to Temple University. We've been working very hard to get the lab up and going. And in June of this year, the DOE project started. So we will be able to work on this for the next 3 years. And we will try to deposit large films and also coat cavities. And at the moment, we are already able to produce good quality films in our smaller reactors. And so this lower field microwave magneto absorption measurement that we've done at Drexel University, it's possible that it might be showing the HC1, then that's a very high value, although we are not very clear whether it is the HC1 that we are measuring in these films. And we have already installed the dielectric puck resonator from University of Maryland. So once we are making large films, we'll be using it to screen the film, and the good ones we'll be happy to send to anyone who are interested in measuring them. Thank you very much.